coming. So I'm pleased to have Hoàng from Wilfrid Laurier University in Waterloo, and expert in graph, induced graphs and
Yeah.
coloring. Right?
Okay.
Yeah, please.
Thank you. I'm very happy to be here. It's my first visit to Korea, so I'd like to thank San Yu for making this possible. So I'm from Wilfrid Laurier University in Waterloo. You know, in Waterloo there are actually two universities. So one is the University of Waterloo, which is a bigger one, right? And Laurier is a kind of smaller university. Not so small, but like we have about 20,000 students. So it kind of mid-range. Yeah. I don't know about Korea here, how big your universities are. I know in some Asian country, a university may have like 80,000 students, right? So, yeah, anyway, so that's where I'm from, and I will talk about coloring restricted graph classes. So, we know there's several very well-known graph coloring problems like the four-color problem, or now called the four-color theorem, which is a famous problem in mathematics. And what I want to talk about is not about that kind of problem, but problem we get by restricting graph, especially by forbidding induced subgraph. So I talk about coloring odd home free graph, coloring even home free graph, and coloring graph by forbidding a finite number of subgraph as induced subgraph. Okay. So for those who don't know, let me try this. Oh yeah, it works. Okay. Okay, coloring is an assignment of integers or colors from 1 up to k to the vertices, so that any two vertices would receive different colors if they are adjacent. So for example, for this graph here on the left, if I click on 3 vertices, and you see that you need 3 colors to color it, because every vertex is adjacent to every other vertices. So that means they have to receive different colors. You cannot avoid it. For this graph on the right, you can see that just by trial and error that you need 3 colors. You cannot color this graph with 2 colors. You cannot. Right? So say you want to color the graph with 2 colors. So you start here at this vertex, you give it color 1 at this vertex, then you need a color 2, right? So for this vertex, say you still want color 1 because you don't want to use a third color. Then if you go to this vertex, then you need a color 2. Then you go up to this vertex and you say, oh, you get stuck. You cannot give it color 1 or 2, so you need a new color, right? So for this graph, we need 3 colors. And this is the C5, right? And this idea seems to be very simple, but it derives to some very, very deep theorem in graph coloring. Okay. So, like I guess most of us know the four-color theorem, which say that planar graphs are 4 colorables. Right? And I think maybe one of the most well-known conjecture in graph coloring that is still open is the Hagwigger conjecture. Right? The Hagwigger conjecture say that if a graph does not contain a minor on the click on T vertices, then it is T colorable. Okay. So the idea of planar graph and minors are about partial subgraph of a graph. But what I want to talk about is about induced subgraph of a graph. Right? So the four-color theorem and the Hagwigger conjectures are about forbidding partial subgraph of a graph. So these are the partial subgraph that are contracted to a click. I want to talk about forbidden induced subgraph. So of course, in this context, perfect graph is I think the most well-known idea, right? So let's formally define that. Say I have a graph G and a graph H. So I say that G is H-free if G does not contain H as an induced subgraph. Right? And then you can lengthen the list of forbidden subgraph by defining a set, right? A set F of graph. So we say that the graph G is F-free if G does not contain any graph of F is an induced subgraph. Okay. There is a very important theorem in this idea of coloring by forbidden induced subgraph, which is a theorem of these four authors. Say you have a graph H, right? And you want to forbid it in your graph. So you forbid H in your class of graph, and you want to know when you can color the graph or not in polynomial time. So this theorem say that if H is an induced subgraph of a P4, a path on 4 vertices, or of a copol, then the problem is polytime solvable, the coloring problem. In any other cases, it is NP hard. Okay, where the copol is simply the union of a P3 and a single vertex. So it is this graph here. Right? That's the copol. Right? The reason why this is called a copol because the complement of it, which is this graph, that is called a pole. Right? So co means complement, right? Okay. And actually, that theorem is even more powerful. So what the proof show is that even if you forbid 2K2, codiamond 4K1 and C5, the coloring problem is still NP hard. Okay, so a 2K2 is just right two independent edges. A codiamond, because that's the complement of a diamond. So a diamond is this graph. Right, diamond. So you forget the complement. A 4K1 is just 4 independent vertices, and the C5 is using the C5 before. Right?
So by coloring, you mean with the minimum number of colors, right?
Yes, yes, finding a minimum number of. Okay, you may notice that sometimes I say NP hard and sometimes I say NP complete, because technically they are not really the same thing, because NP complete means it's NP hard and the problem is in NP, right? Where a problem is NP high, it is as high as any problem in NP, but it may not be in NP. Okay. You don't need to make this distinction, but I will say NP hard, NP complete. Okay. But this theorem implies that it is NP complete, NP hard to color graph with no hole sublet at least 5. A hole is an induced cycle, right? Because if you have no 2K2 and no C5, then you have no C6, no C7, and everything. Right? It's also NP hard to color odd home free graph. So these are the induced cycle with an odd number of vertices. It's even NP hard to color P5 free graph. So there's not much we can do, right? In some sense, but you see, there's still a lot of nice about it. So a graph is perfect if for every induced subgraph, the number of colors you need to color it, the chromatic number, denoted by chi of H, is the same as the size of the largest clique, the number of vertices in the largest clique. You have seen that if you have a clique of size k, you need k color. You cannot avoid, right? So perfect graph are the graph where this is best possible for every induced subgraph. Okay. And there is a very important theorem that was proved by Lovas maybe like 50 years ago in 1972. A graph is perfect if and only if the complement is. This is and the proof is absolutely beautiful. It's like a one-page proof. If you have time to read it, I would recommend you try to read it. And even more important is a theorem by these three authors, where they show that given the perfect graph, there is a polytime algorithm to find a minimum coloring. That's this number. To find a largest clique. Alpha G is the largest clique in the complement, or the stability number, and the chromatic number in the complement. And this algorithm is not a structural algorithm in the sense that it doesn't care what the structure of the graph is. It just uses some very deep property of mathematical programming and polyhedral theory on perfect graph, and that were developed by Fulkerson and Vachequatan and so on. Right. So, but anyway, for perfect graph, we know we can find algorithm. There's an algorithm to do these things, and maybe then we can find a more combinatorial algorithm for our class. Right. This would be the theme of this talk. Okay. So, so a hole is an induced cycle with an odd number of vertices, which is at least 4. So say this is C5 and C7, and the hole you go on C9 so on. That's called an odd hole, and an anti-hole is just the complement of a hole. And it was conjectured by Claude Berge in the early 1960s that a graph is perfect if and only if it does not contain as induced subgraph an odd hole or an odd anti-hole. Right. So if a graph has no odd hole, no odd anti-hole, you can color it with the size of the clique number of color, and we know that's the best possible we can hope for. Right. So this theorem and the previous theorem, this one, I should say something about the polyhedral reason, but okay, it's too late now. Just say that perfect graph are a graph natural class of graph to work on, right? Okay. But okay, you can say something that are still very interesting, even though the strong perfect graph conjecture have set the high bound for the chromatic number. You can still say something about the structure of graph without odd hole. So, I will say that a graph is 2D divisible if for every induced subgraph with one edge, I can partition the vertex set into 2 parts, where the largest clique in the graph must meet each of the parts. So in a sense, for a graph, it is 2D divisible if I can partition it into 2 sets where every bigger clique has to hit both parts. Okay. So if every biggest clique has to hit both parts, then I know that each part has the clique size of it is smaller, right? At least by at least 1. I know that. Right? So if you do induction on the clique size, then you know that if a graph is 2D divisible, then the chromatic number is bounded by the function 2 to the omega.
So this should be strict, I guess.
Strict inequality. Right? Equality should be removed.
Strict.
Okay, that's a typo. Yeah,
Yeah.
thank you. Yes.
Otherwise, it's trigger.
Yeah. You have to take away this thinking.
Yeah.
Okay. I should fix this typo. Yeah, thank you. Yes. Okay. Just think about the picture. All right. Yes. Should be strictly. Yeah. Otherwise, there's no induction involved. Okay. Think about it a little bit. Then perfect graph are 2D divisible. Okay. Perfect graph 2D divisible. Odd holes are not 2D divisible. So think about the C5. You cannot divide into 2 parts, where each part is a stable set. Why? Because in the C5, the largest clique is an edge, right? And if you can divide the C5 into two parts where each part has no edge, that means the thing is two colorable. But you see the example that the C5 is not two colorable, right? Okay. So with a Colin McDermott, we can conjecture that a graph is two divisible if and only if it is orthogonal free. Okay. So we conjecture this in around about 1993, 94. So it's like maybe 30 years old. Okay, and it's not been disproved yet. Okay, I don't know if it's true or not, but it's. Of course, this conjecture implies that for an orthogonal free graph, the chromatic number is at most 2 to the omega, right? For the reason I just explained.
2 to the omega minus 1 or?
Yeah, you can play with it. Yes.
Okay.
Possibly, yeah, 2 to the omega.
In the
minus.
previous pages.
Yeah. Scott and Seymour proved that orthogonal free graphs have the chromatic number at most 2 to the omega. Okay, so well, it's still a big gap, right? But in these kind of problems, you always want to find the forbidden subgraph in polynomial time if you can. So an orthogonal free graph can be detected in polynomial time, and so far there's at least 2 algorithms for doing that. Okay. But there's other, okay, so the big conjecture, orthogonal free graphs are two divisible, that's still open. But there are some partial reason, like if you forbid a banner together with an orthogonal. So a banner is this graph here. That's a banner. A previous theorem by these 4 authors say that if a graph is K4 not home free. K4 means the click on 4 vertices. That is two divisible. P5 and C5 free graph are two divisible. Dark and orthogonal free graph are two divisible. A dark is this graph. Like you take an arrow, you shoot at somebody, you know, like that, right? Okay. Okay, and I want to talk about the techniques for solving these kind of problems. So let me just define a homogeneous set in this way. So take a graph like this, and look at the C4 here. So the C4 is homogeneous because it has at least 2 vertices and there's something outside it. And every vertex outside it either see everybody inside or see nobody. So this vertex see everybody in the C4. This vertex see nobody. So that's called a homogeneous set. Okay. The idea is when you have a homogeneous set, then you can decompose the graph in a natural way and you can recursively solve your coloring problem or your click problem in the smaller graph. And the decomposition is really natural if you think about it. So you decompose it into 2 graphs. One graph is your homogeneous set, the C4 here. The other graph is the graph you get from the original graph by constructing the homogeneous set into one vertex, like here. Right? So in finding a largest click, what you can do is you can find the largest click in the homogeneous set and encode it as a weighted vertex in this graph, and then you solve the weighted click problem. Right? So it is a smaller graph, so you hope you can do it. If you keep doing this, then you can do it. Right? For coloring, it's a bit more complicated, but you can do the same for coloring. So that's the ideal homogeneous set, and this plays a very important role in the perfect graph theory. The proof of Laurier's theorem that a graph is perfect if and only if the complement is use this fact here. on homogeneous set. Okay. And we see something like that. Let me show you like the structure of the graph and the way people prove it. So let's say I want to prove that a graph without banner and odd hole is 2 divisible. So a banner this graph, right? Then we can prove that in this case either the graph is perfect or the stability number is at most 2, or it contains a homogeneous set. So as I mentioned before, if you have a homogeneous set, you're done because you do it by recursion, right? If you are perfect, you are done because by the strong perfect graph theorem, the thing is 2 divisible. What if the stability number is 2? The largest stable set has only 2 vertices. How can you solve the coloring problem or whatever problem? You take the graph and you look at the complement. So this is the graph, this is the complement. The complement is triangle free, right? No triangle. Then in the complement you find a maximum matching. You use Edmond theorem to find the maximum matching. So the maximum matching over here will correspond to an optimal coloring on this graph. You see? So it's like a trick, but it works. Okay. So without matching, I think it would be really difficult, right? And so it only works when alpha is almost 2. Okay. So for odd hole free graph, coloring is NP-har. Finding a larger clique is NP-har. Finding a minimum cover is NP-har. This is from previously known result. But the stable set problem is unknown. I mean, finding the largest stable set in the graph is unknown. Okay. And actually, there is even a stronger structural property that may work in this case. So I say that the graph is perfectly divisible if there is a set X, so that X meets on the largest clique of the graph and X itself induces a perfect graph. So for example, so it would be like a 2 divisible graph, except that the set X here is perfect. Okay. Then you can use induction to prove that a perfectly divisible graph has a chromatic number at most omega square, where omega is the size of your largest clique. So it is a stronger property, right? Because if the graph is perfect, then you color it with omega color, right? After you color it, then on this side your omega is decreased by 1. So by induction you do it again. Oh, not induction. You do it by iterations, right? Then yeah.
So you didn't care about constant, right? So it's maybe,
No.
like divided by
No.
2.
Here there's no constant, right? Here just omega square, because okay, this part is perfect, so I color it with omega color.
Yeah, so it's
Now
omega plus-
here the clique size is now at most omega minus 1.
Yeah.
So I repeat. Oh yeah.
Yeah, so
that could
I
be
was thinking
something.
that
Yeah.
it's omega
Yeah.
minus over 2, right? Almost 2.
There
square
could
over
be.
2, right?
Yeah. That could be. Yeah. That could be. Yeah. Okay. So most of the classes that I mentioned before are not only 2 divisible, but they are perfectly divisible. Right? Okay, so these are the reasons. I won't define these classes, but there are people who have worked on this. I think the interesting reason here is by Wu and Shu. So they prove that fork and odd balloon free graph are perfectly divisible, where a fork is this graph, and an odd balloon is it's like you take a hole and you add a pendant vertex, where the number of vertices is odd. Okay, so but they make a conjecture which is really interesting. which is the conjecture that for free graph are perfectly divisible. It has nothing to do with odd hole. I conjecture that odd hole free graph are perfectly divisible. Actually, I didn't make this conjecture. I just pose it as an open problem. I just asked like, can people find odd hole free graph which is not perfectly divisible? I didn't want to call it a conjecture because it's like very ambitious. But then people wrote about this and they say that I conjecture it. So now I say, okay, I conjecture it. So the first paper about it is not a conjecture, it's like an open problem. Okay, but now it's a conjecture. Okay, so this means if the conjecture is true, then for ortho-free graph, you can color the graph with omega square color. Okay. That would be like very hard to believe, but it may be true. Okay.
Is there any lower bound for the chromatic number for alcohol free graphs?
I think the best lower bound I know is close to omega square. I don't know if it's exactly omega square or not. What you do is you take graph with alpha equal to 2. So with alpha equal to 2, the only odd hole you can have is a C5. You have no other odd hole.
Okay.
And then you, okay then. I think there's some bound on that, yeah. And also the problem with this is, it would be like a Ramsey theorem for graph without triangle. It's almost the same except for the C5. And I know nothing about this structure, the Ramsey theorem. I mean, if you just forget about the C5, just think about the Ramsey number for triangle-free graph. It's almost omega square, right? Because the number of vertices is, I mean, you take a graph of n vertex without stable set of size 3. Then the Ramsey theorem say your clique had to be close to square root of the number of vertices or something like that, right? But that's not take into consideration the C5. So you need a Ramsey theorem for C5 free graph to do this. Okay. So even hole free graph is just the other side of the coin. So now an even hole is a hole with an even number of vertices. Right? And there are polynomial-time algorithm to recognize this even hole free graph. There's many, as you can see. There is a nice theorem by Junosi and Seymour. They prove that an even hole free graph contains a bisimplicial vertex. So this is a simplicial vertex where the neighborhood is partitioned into two cliques. Can be partitioned into two cliques. This is called bisimplicial. And the corollary of this is that you can solve the clique problem on even hole free graph. Okay. I want to mention a very well-known theorem of Faber when he showed that a C4 free graph has at most order n square maximal cliques. Maximal is meant with respect to set inclusion, not size. Okay. So the complexity of coloring even hole free graph is unknown, but there are special cases where you can color this graph in polynomial time, like if you forbid, say, a diamond or a kite or thing like that. Okay. So this is the current status of this problem. So for perfect graph, you see for this clique stable set, coloring and clique cover, everything is in P. For odd hole free graph, the only open problem now is stable set. Right? For even hole free graph, the three of the problems are unknown. Okay, what happened? And okay. And only the clique problem is solved. Okay. All right. Now I want to talk about a different kind of problem. Well, it's the same kind of problem by forbidden induced subgraph, but it's a different way to see the problem. So let's say I look at on graph on 4 vertices. Let's call this class F4. You can see that 11 graph on 4 vertices. Right, 11. And let's say I choose an arbitrary subset of these 4 vertices to forbid. Right, so I want to know what is the complexity of the coloring problem. If I forbid a subset of these vertices, there's 11 graph in this, so 2 to the 11, so that's like 2000 something problem, right? 2 to the 10 is 1024, so 2048, okay, problem to solve. Actually, there's only 3 problems left. So all those 2000 problems have been solved. Okay. So this is like a lot of theory involved by the community. So no single person proved this. But from what we know so far, there's 3 open problems. So if I forbid a 4K1 and a claw, I haven't drawn the claw here, but I think it's the most famous induced subgraph, right? If I with a claw and a stable set of 4 vertices, it's unknown. Forbid a claw, stable set of 4 vertices, and the complement of a diamond, complement of this is unknown. Or forbid a 4K1 and a C4. So those 2000 problems now reduced to 3 open problems. Okay. And this problem actually may be very difficult. I don't want to be pessimistic here. The reason is, remember how we color graph with alpha equal to 2? To color it, you look at the complement and you find a matching. You know, the algorithm to find a maximum matching is not trivial, right? It's not trivial. But these 2 problems generalize graph with alpha equal to 2. So if you solve it in polynomial time, that means you find maybe a different or more powerful algorithm to find a matching in a triangle-free graph. And now more than triangle-free, right? Because all of these graphs contain a stable set of 3 vertices. So it generalizes graph with alpha equal to 2. Okay. And this problem is really interesting to you. Forbid a 4K1 and a C4 is still open. Okay. Let me show you just like a little bit of how the proof in these things work. So it's the idea of click width. So you say you have a graph and you want to build it with a certain operation. You cannot just build it in the way you like. There's some restricted operation you have to use to build a graph. And the operation is you can create a new vertex and you have to give it a label, L. You can take the disjoint union of 2 label graphs and you can say I want to join every vertex with label I with every vertex with label J. We'll join my edges. Okay. And I can say I want to relabel all vertices of label I to label J. So the click width of a graph is the minimum number of labels that you need to build this graph. Okay. So it may sound complicated the first time you see it. Let me show you an example. Let's say I want to build a path, a long path. Okay. So for a path on 2 vertices, that's easy, right? Vertex label 1, vertex label 2, make a join between 1 and 2. Right? Say now I want to build a path on 3 vertices. That's easy too. I introduce a new vertex with label 3 and I say join 2 and 3. Easy. Right? Now I want to build a P4 with with only 3 labels. What do I do? Okay, easy. I have the P3, I relabel 2 to 1, I'm allowed to do that one operation. So now 3 is now a unique label. So I introduce a vertex with label 2 because 2 wasn't used before. I say join 2 and 3, right? And I relabel 3 to 1. So you can see in this way I can make a path as long as I want with 3 labels, right? Okay. So why is this interesting? It's interesting because, well, if a graph has bounded tree width, then it has bounded click width. So click width is in a sense a generalization of tree width. And if a graph has bounded click width, then the complement also has bounded click width. And then if the click width of a graph is bounded, then the chromatic number can be computed in polynomial time. And actually, I don't know who was the first to prove this. Maybe you know. I'm totally confused. There's several papers written on this. The paper that I know the most is by Rao.
Yeah, I think it's around.
And he mentioned this explicitly.
Yeah.
The other paper don't mention it explicitly. Right. So this is why we are interested, because we know if a graph has about the click width, then we can compute the chromatic number. Right, so that's the reason. So let me show you like an idea of how the proof in this reason go. So let's remember this problem. Coloring of 4K1 C4 free graph is, we know right now nobody know how to color it. Yes.
Sorry, I think I got confused. So your previous, can you go to the previous
Yes.
slide? Third point says chromatic. So does it mean that chromatic number of P5 free graphs is polynomial time? Because you said P5 free, like PK free graphs.
We talk about a class of graph, but P5 is just a fixed graph. With a fixed graph, I know the click width is fixed.
Yeah, that's
Right.
why I'm confused. So you also mentioned that for P5 free coloring
Yeah.
is NP hard.
Yes,
Right.
but this means P5 free graph have unbounded click width.
But I thought you said PK.
P4 free graphs.
Ah, okay, sorry, just the PK. I'm sorry. Yeah,
Right.
sorry.
Yeah, okay.
Sorry.
Yeah, okay. No problem. Okay. All right. So we don't know how to solve the coloring problem for 4K1 and C4K. So in math, what do? You give more restriction, right, to the problem, and hopefully you can solve it. So let's say now I want to forbid the C5 too. So no 4K1, no C4, no C5. Then there's a theorem that say that this graph is either perfect or has bounded click width. And so we know how to color it. Right? And actually I want to mention even a nicer theorem by Irina Benet, where she replaced the C5 with the C6. And this is more interesting because this is a class of graph without even hole. Right? Graph with no C4, no C6, no 4K1. A graph without even hole. So in a sense, she showed that an even hole free graph without a 4K1 can be colored in polytime. Right? But I want to show you like how this proof goes in this case, because you can make a lot of variation on the problem, right? So what we prove is for this class, no 4K1, no C4, no C5. If it has a C7, then it has bounded click width. If it has no C7, then it's perfect, right? I mean, this graph, if it has no C7 and no C4 means no odd anti-hole. Right? So how do we prove that if the graph has a C7, it has bounded click width? Okay, I don't have time, so I won't go over that thing. I will just try to explain to you now how do we prove that if a graph has, in this class have no C7, it has bounded click width. So what you do is you take the C7, you look at the neighbors of the C7. So you group the neighbors two sets that have the same neighborhood on the C7. So there could be 2 to the 7 subsets, right? There are vertices with no neighbors, there are vertices with all neighbors, there are vertices with one neighbor, right? So on. Of course, you can reduce this. So let me just give one example. Let's say I look at a set that sees 3 consecutive neighbors, 8, and another set that sees 3 consecutive neighbors, which is just one step to the right. So this set here, B. Okay. So I know right away that there has to be OSJ between A and B. So A has to be complete to B. Why? Because if not, I have a 4K1 like 1, 2, 3, 4, right? So just look there and say, okay, there has to be all edges. So you do this analysis for every pair of neighbors. So this one here, this set, now maybe you can shift it to the right again, and you do the analysis. So for example, if you shift the set B 2 steps, you get this situation. And now we know there can be no edge between A and B. A has to be anti-complete to B, because otherwise we have a C4, right? We're in the class without 4K1 C4. If I have this edge, I have a C4. So there's no edge. The problem is if I shift B only one step to the right like this, then I cannot do anything. Between A and B, I could have any kind of edge. Because I cannot find a 4K1, I cannot find a C4, I cannot find a C5. Okay, so that's bad. But the only good thing is B is the only set that can be bad in this respect with respect to A. Okay, this of course we have to prove it, right? So I mean, the proof is if there is another set C that is also bad to A, then I have to find the forbidden subgraph. Okay. But the good thing is everything just works out in this way. So this is the idea that we say about the uniform partition. So say I have a partition of the vertices into K set, right? So let's see. So let's say I have a partition into K set, and I say that Si is uniform to Sj if, say, between Si and Sj, either I have all edges or I have no edge. Remember the idea of the homogeneous set before? It's exactly like that. That's the idea of homogeneous set, more general, but more generalization. And then I say that a set I is near uniform if everything else is good to it. Only one can be not good to it. Okay, so I say this is a near uniform partition. And the thing about working on this problem is actually not proving the problem, but making the tools to prove the problem. I think the tools are more interesting than the result itself. So this is the tool that we say. So we say that if a graph, the theorem say if a C4 free graph has a near uniform partition with K set, then the click width is at most 2K. Right, so this is the tool. This is why the idea of click width works, right? Okay. So okay, so I want, and I just want to show you a different tool which is even more complex, which is again just illustrate why the tools are more important. So say now I want to work with graph without 4K1, C4, and P6. I want to prove that I can color the mean polynomial-time. And the idea would be to have a tool which is more general than the near uniform partition, which is a little bit more complex, but Okay, so I say that a set X is monotone to Y if any two vertices in X have comparable in Y. So say X and Y. So if any two vertices in X have comparable neighbor, comparable means the neighborhood is contained in the order one and right. So that's called a monotone set. Right? So essentially we prove that if a graph admits a monotone partition with some special condition which is a little bit complicated. With this property, very extreme vertex. It just means that if I take a maximal vertex in X, then it has to be uniform to the rest of the graph. Or if I take a minimal vertex in X, it has to be uniform to the rest of the graph. So this idea generalizes this idea of uniform. So what we prove is,
So by uniform you mean it's complete to Y or incomplete?
yeah, so everything else complete to it or not seeing it. Right. Yeah. So it generalizes the idea of the uniform partition. So we prove that actually if you have K set, then the click width is K plus 1. It's even better than the previous theorem. So the hope here is for this restricted graph of classes, you have better tools and maybe eventually you can prove the whole thing, you know, maybe or maybe not. Right, okay. I want to talk very briefly about the role of the claw in this thing because that's very important. Right? So the first two open problems have something to do with the claw, right? And you know, of course, claw-free graphs are very well studied, right? I think it's the most well-studied class of restricted graph, right? Like, you know, finding the stability number of claw-free graph is a very well-known problem. It actually is generalized matching, right? Things like that. So, so we call claw-free graph generalized line graph. So you know what is a line graph? A line graph is, say I have a graph G. So the line graph of G is simply each vertex corresponds to an edge. So this vertex corresponds to that, this vertex corresponds to this vertex corresponds to this. Right? And two vertices are adjacent in the line graph if the two edges here are incident. So the line graph of this graph is this graph. Okay? Okay. There's a very well-known theorem of binary. Let's say a graph is a line graph of some graph if it does not, if and only if it does not contain any of these 9 graphs as induced subgraph. And you see here that the claw plays an important role. Right? The claw is thought of it as like the main character in this list. But there's others. Right, that's all. Right. Okay, I won't go over the detail because I just want to mention some problem. So for example, there's a theorem that say, I should say, you know, Wissing theorem, right? For a line graph, the chromatic number is at most delta plus 1. Delta is the maximum degree. Right? That, and is that delta omega? I think delta. And there is a beautiful theorem of Kickstad which say that if a graph is claw and k phi minus e free, then k is about delta plus 1. Is it omega? I think it's omega.
I think you should replace it with omega.
So omega, sorry.
It becomes the degree.
A typo, yeah, because it's the
maximum that thing you wrote is true for every graph, right?
Yeah, sorry. Maximum degree, maximum degree corresponds to largest click.
Yeah.
Omega, okay. Replace this by omega, right? So the nice thing about Kickstad theorem is it's generalized Wissing theorem, right? By this list, right? So So we ask, what if now in the problem what I cannot solve? Law and for one thing, what if I introduce the Gstad graph k5 minus e? Then I can solve the problem in polynomial time. Right? So let's go back here. So think about our problem. We forbid for k1, we forbid law. If we forbid k5 minus e, we know how to color it. Then you can look at this list. You can say, okay, you know, maybe I can play this game. I just look at each graph, I forbid one and see if I can solve it. Right? And why would I do that? So for example, in this list, only 3 graphs have a k4. This, and this. Then this one has a k4, yes. This, and this. So you may ask, okay, what if I forbid one of these graphs? So what is known is if I forbid co-R, then I can call it in polynomial time. If I forbid bridge, then I don't know how to do it yet. Okay. But if I forbid the bridge and the C4 twin, then I know how to color it. And if you think about these 3 graphs, they belong to a family which is called the whole twin. So you take a whole of like at least 4, and you just duplicate the vertex. So the graph has no whole twin. So if I forbid them, I know how to color them. So the only remaining case are like this, and this. The 3 remaining cases. So maybe, but these are maybe doable problems, you know, like they may be like not impossible. So as I mentioned, if I forbid whole twins, I know how to color it. If I forbid the graph co-R, it's called co-R because in the complement it looks like the letter R. Right, that's one. Okay. I don't know how to do the bridge, but if I forbid a C for twin, then I can do it. Okay. Okay. I want to mention an important reason by this author would say that if you forbid a claw and a CK for the fixed K at least 4, the coloring problem is NP complete. Okay. So these are the 3 open problems left. In the class plot for the one fish are the bridge graph, the 5 wheel, and the co-A. Right? Here. Co-A, bridge, and 5 wheel. Right? So, of course, when you forbid this graph, you have to justify it, right? Because what is the justification? So here, I think for these 3, it makes sense because they can belong to the same family, the whole thing graph, right? For these 3, maybe you say, okay, because these are the graphs that contain the K4, the other one don't. Okay. Now for these 2, you say, okay, because these are the leftover, and I just want to know the answer. Okay. All right. So, okay, so that's it for it. Thank you very much. I'll be happy to answer your question.
Thank you. Any questions?
Yeah.
So for some of your theorems, you can color it, but it would be nice to avoid like the ellipsoid method. So you have the perfect graph as an outcome,
yes.
But maybe you can color it without.
Okay.
using
Yeah,
the
I skip
ellipsoid
over
method.
it. Yes, there. In all of the cases, we can avoid that that algorithm by using the ellipsoid method.
Okay.
Yeah, you can use just structure techniques
Okay.
to do it. Yeah. But okay, I should say, even for click width, I don't understand it. So that's a theorem would say, if a graph has about the click width, you can color in polynomial time.
Sure.
I don't understand the algorithm. It's very complex because I mean it uses some kind of logic, second order, and then eventually I'm sure it reduces to dynamic programming.
Yeah.
Right?
Yeah,
Eventually.
I think it's dynamic programming.
It's dynamic programming. It's like 3 width. It's almost, yeah. But you can say maybe it's more understandable than the ellipsoid method.
Yes.
I don't know. I don't
think
know.
so.
Maybe you still know what is going on with the dynamic programming, whereas with the ellipsoid method, you don't know what's going on. You know, it will split out an answer, but you don't know what.
Mhm.
Okay.
Do you have some estimate, like what is the most, like for the running time when you have a polynomial time algorithm, maybe like some problems may have n to the 100, some problem may have n to the 5, or
The thing is, with the click width thing, what is the complexity?
Oh, right. N
Because-
to the k.
It always reduces to bounded click width, right? So we cannot avoid it. There's some
Ah,
other
I
cases
see.
when we can do very quickly, like n to the 4th or n to the 5th. But then there's a case where the click width is bounded and we have no choice.
I see.
Yeah.
Can you? I mean, I was curious about this near uniform partition.
Yeah.
Like, can you sketch some idea for the proof, or
Ah,
I don't know.
only okay. I think this
Oh,
I can.
why? Yeah, this thing. Like,
I think
why?
it's easier than the near uniform partition.
Yeah.
So let's just think about this uniform partition first and do near uniform. So uniform partition means okay. So means so I fix my attention on the set S1, right? So everything else is uniform to it, meaning everything else either has all edges or has no edge, right?
Mhm.
Then I do it by induction. I remove it, and by induction I can build the graph. And not only that, I require that these set have different labels. I can require that. So say this has label 1, label 2, and say label 3.
Mhm.
Right? Now how I can build this? You can see, right?
Yeah.
I say, you know, make all edge between this label and that, right? And if there's no edge, I don't have to do anything. If there's an edge, I will say, okay, make join label 1 to label 3. Okay, not 1, maybe that should be 0. Right? Boom. Right? Now with near uniform, now it's a bit more difficult because near uniform means it's still doable, like this. Okay, so near uniform means I have one set with one other set is not uniform to it, but every other thing else is uniform to it. Right? That's what near uniform means. Right?
This is for every.
Yeah. Because if this set is back to it, then it's vice versa. Right? So if A is near uniform to B, then B is near uniform to
Yes,
A,
yes.
and everything else has to be good to it. So you
Right.
can see the point now. So by induction, I will do this with label from 1 to K. And I build this with label K plus 1 and label K plus 2. Because here, even though it's near uniform only, but it's C for free. C for free means, okay, this, okay, I should say these are clicks, right? Did I say that these are clicks? Okay, I think the set have to be clicked.
Oh, okay, clicks.
I think I missed, yeah. So then, because,
I see. Otherwise, it doesn't make sense.
yeah, they have to be clicks. Otherwise, they can be anything then.
Right.
Yeah. You cannot do
Yeah.
anything.
You can start with
Yeah,
some
yeah,
graph with
yeah.
large clicks.
Okay, I think this should be into clicks, but yeah. So then you see how I do it, right? By induction, I have these labels, and then I build this graph. I can do it because any two vertices are comparable here. So I will have the set of maximal neighbors, and this guy dominates him, right? This guy dominates him, and maybe this guy is dominated by everything. So I build these vertices first.
I see.
Maybe the twin width is even bounded.
Bounded clicks implies bounded twins, right? So
Yeah. Yes.
So
Yeah, that's true.
yeah, so this implies foundation.
Yes.
Yeah, that's true.
Yeah.
Yeah, but I guess, yeah, probably,
Yeah.
yeah,
Mm.
that's right.
Yeah.
Okay. All right. Any other questions? So if not, let's thank the speaker.
Okay. Thank you.